My name is Paul Byrne. I am a professor of planetary science at Washington University in St. Louis. I'm a geologist by training, but I am really interested in why planets look the way they do. And that's led me to studying worlds as diverse as Mercury, the smallest planet in the inner solar system, all the way out to Pluto, and increasingly to exoplanets, that are planets orbiting other stars. Basically, I just want to understand why planets look the way they do and what that tells us, especially about our own world, why Earth has remained the way it has, and why it looks the way it does for as long as it has. So they sort of are, and I'll tell you there's two reasons why. So one is those really large planets, well, actually three. Yeah, this is where goes to a long hour-long answer, which I'll try and give you the cliff notes. So one of the things that we want to know is why are the giant planets where they are, and what impact, if any, and probably there was an impact, did the formation of those planets and where they are govern why and where the smaller worlds like Earth are today? The second question we have is what's inside these worlds. So we've explored Jupiter and Saturn, which are the two biggest ones, fairly well compared to some of the rest of the places in the solar system. I don't think we would describe them as well understood, but we understand them better than other places. But there's two other worlds farther out from Jupiter and Saturn, Uranus and Neptune. And we sometimes call them ice giants, but we don't actually know what they're made of, and we don't know what their interior structure is like. And it's even possible that there is a large, what we call a super Earth, like an Earth-sized rocky world, or even bigger than Earth, deep inside these worlds, surrounded by some sort of weird ionic water slushy mix, and then a big thick atmosphere of hydrogen and helium. We don't even know that because we've only ever sent one spacecraft to those worlds. And the third reason why I'm so interested by the giant worlds is that they all have rings and they all have moons. And some of those moons are bigger than Mercury. They're bigger than the smallest planet in the inner solar system. So they are planets by their own right. We just call them moons because they go around bigger things than them. So there's a whole pile of reasons to be interested in what we call the outer solar system as well as the inner solar system. So I would say generally I'm fairly game for anything that we would call a planet. So in the case of the Messenger mission, it took 6.5 years from launch at Earth before it finally actually made orbit of Mercury. It reached Mercury sooner, but it was going too fast every time. So it had to do all these flybys to slow it down and circularize its orbit and eventually get to the right point where the engineers would fire the engine and it would get captured into orbit. And we were in orbit then for more than 4 years. Originally, the plan was to be there for 1 year. We operated for about 4 years and 1 and a bit months. And in that time, we took images of the entire surface. So we were able to fill all the gaps in that Mariner 10 had found. And we were able to discover so much about Mercury. And I can tell you a whole lot of interesting Mercury facts, but the biggest thing is that it really became its own world in its own right. That previously, to most people, it's a little bright light in a telescope. And of course, you cannot point powerful telescopes like Hubble or Webb at Mercury because it's so close to the sun, you risk damaging those telescopes. So this is a world that really is very challenging to observe. It's very challenging to get to. But once we got there, we made sure that we got our money's worth of that spacecraft. We operated for 4.5 years, and we took so many images. We took chemical measurements, we took geophysical measurements, we did a whole pile of science that we're, like I say, we're still working through now, which it just tells you just how much value that mission returned. We often think about Venus as Earth's evil twin. The reason for that is it's a reasonable thing to call it. The surface temperature at Venus is something like 800 Fahrenheit. The surface pressure is the equivalent to about a half mile under the ocean on Earth. I mean, this is the normal daytime temperature pressure, although it's actually the same temperature at night. Venus is literally a planet that's essentially hell made real. And so what that has meant is, although we've sent lots of spacecraft, humans have sent spacecraft to Venus, particularly in the 1960s and 70s. Many of those spacecraft, the ones that worked when they got to the surface, only lasted about an hour or two before the high surface temperature melted all the electronics. So this is a world we don't understand very well. And the reason I find it so fascinating is there's one principal reason. There's a whole pile of science that I'm interested in, but it all gets wrapped up in one umbrella, which is that Venus is almost the same size as Earth. It's made of probably the same stuff in about the same amounts. It orbits the same star. It's the same age. It doesn't get very much more. It gets about twice as much sunlight as we do. And yet it is vastly different to what we see on Earth. It's nothing like it. The surface is covered in lava plains. There's volcanoes all over the place. There's these huge highlands that might be like the continents on Earth. We don't know. It's got an atmosphere that is made of CO2, so it's almost the same atmosphere composition as Mars, but this stuff is impossible to breathe. It's in what we call a post-runaway greenhouse, so the surface temperature is extremely high. There's a global layer of sulfuric acid clouds, which is not great. It is worth pointing out, and this is relevant to the balloon I'll talk about in a moment, that actually if you go to the atmosphere, at about 40 miles up, the temperature and pressure are actually room temperature and pressure, as in what we have on Earth with shirt sleeves. So the only other place in the solar system that is room temperature and pressure is actually about 40 miles above the surface of Venus. There are sulfuric acid clouds. There's ways to mitigate that. But if you had like a plastic little suit on you and you had an oxygen mask, you would otherwise be safe, which is not the case. You would need a spacesuit virtually anywhere else in the solar system. But what interests me is why Venus, for all these apparent similarities in a broad sense in terms of size and bulk composition and stuff, is why it's not like Earth. And this is particularly relevant for two big reasons. So it's important to understand this for Venus, for the sake of Venus itself. But the two big reasons are, one, we don't understand how our own planet has remained what we call habitable and hospitable for billions of years. But we know that it has. We don't know when life emerged on Earth. We know there was life here, there was well-established life here 3.5 billion years ago. The planet's only 4.5 billion years old. So potentially for many hundreds of millions of years before that bit that we can see in the rock record, there may have been life on Earth. So understanding how the planet has managed to develop habitable conditions and then keep them is a huge focus. And more tied to that, but the other part of the other second reason it's so important is because we're discovering more and more rocky planets orbiting other stars. And we're beginning to get good at finding Earth-sized worlds. And sometimes there's a press release where a scientist will say they found an Earth-like world. But it turns out that we know of no other Earth-like world where Earth-like means actually like Earth, liquid water on the surface. We have found an increasing number of Earth-sized worlds, but we cannot tell yet if they're going to look like Earth, with liquid water oceans and squirrels and trees, or if they're going to look like Venus, just dry, super hot, basaltic lava flows everywhere. So we don't know why you get one or the other of those two outcomes. And what's going to be really important in the years ahead is if we discover more and more of these Earth-sized worlds, we will begin to learn how many of them are like Earth and how many of them are like Venus. And that raises the possibility, it raises the question that maybe we're framing it wrong when we say why is, we think of Venus as Earth's evil twin. Maybe that's the wrong way to look at it. Maybe Venus is the more common outcome. And maybe for some reason we've yet to discover, Earth is actually Venus's calm and happy twin. And so the point is that it ties to the idea of like, how do you end up with a Venus versus an Earth? And the only way you can answer that question is by going to Venus and understanding its own climate and geological history. In 2020, almost exactly 5 years ago, there was a claimed detection of a gas in Venus's atmosphere that certainly on Earth is almost exclusively associated with activity from biological life forms, from some sort of bacteria that process a gas called phosphine, which is otherwise quite toxic, but it is a gas that we know turns up in swamps, for example. And so that turned the attention back to Venus from something that people going back to Carl Sagan in the 60s had proposed, that perhaps because, like I said earlier, the upper atmosphere of Venus above the clouds is between and in and above the clouds is room temperature and pressure. Could it be that may be another abode for life? Certainly even modern life, where life is still around today. And so this has sort of led to a analysis and a reassessment of Venus as a potential astrobiological target. So if we were to design, for example, a balloon, which is the concept that I've been working on with colleagues at JPL and others, the idea is that we would fly this balloon, which we call Phantom, which is this large helium-filled balloon. It's actually two balloons, one inside the other, and it actually allows us, by exchanging gas between the two, we can actually change the altitude that we fly at. But this balloon is otherwise just passively carried through the skies. We would instrument it. We would put instruments on it that would be able to tell us about the chemistry of the atmosphere and the composition, the physical dynamics, and if there's wind. And there's a host of other things you could do too, including the surface, the interior, and even the atmosphere and how the atmosphere is lost to space. You can do all those kinds of investigations from a balloon. I like to say to people that balloons, or we call them aerobots, an aerial robot, which sounds a bit more technical, because it doesn't have to be a balloon. It could be a blimp, or it could even be an aircraft of some kind. a fixed-wing aircraft, but an aerobot is to Venus as rovers are to Mars. There are things that will allow you to be mobile, and there are things that will allow you to operate for months or even years in situ, measuring stuff that you cannot do remotely, either from orbit or from Earth. So a big part of what I do these days is helping develop this concept and advertise this concept and think about the science you could do with a concept like this, where we would fly a Venus aerobot, this aerial robot at Venus, as a sophisticated balloon designed to operate in the clouds. We would be able to make it resilient to sulfuric acid. We would put all the right instrumentation on board. It would have solar panels for power. And this thing would basically circle the planet passively, carried by the winds. And it would take between 7 and 5 days to go to do one revolution of the planet, depending on the latitude. Slowly for months or perhaps even a year or longer, spiraling toward the pole, constantly taking measurements and giving us a view of Venus, both literally and figuratively, that we've simply never had before, and covering the kind of distance that only we could dream of with rovers on Mars. So that's been a big part of the science and the time I spend doing things. It's both developing this idea for this concept, but also thinking about what are the science questions that we can answer, including why Venus is the way it is and why it seems so different to what Earth is.